Earth is the only planet with plate tectonics. It has an abundance of internal heat and liquid water. The heat causes Earth's surface to deform. Earth's lithosphere doesn't become too cold, so it can move. Mars and Venus are single-plate planets. Mars is smaller than Earth, so it has cooled at a much faster rate. Mars's lithosphere has become very rigid. It cannot be broken into plates. Venus is about the same size as Earth, but internal heat alone is not enough to move the plates. There is no water in Venus' interior. Although Venus is volcanically active, its surface doesn't flow. Mercury lost most of its mantle early on. It cooled down to form a solid uniplate planet. On Earth, interior water lubricates the tectonic plates. Internal heat combined with water enables Earth's plates to slide. There are 7 major plates that make up 94% of the Earth's surface. They flow, collide, spread apart, uplift, and subduct. Continental drift broke apart supercontinents many times in history. Pangaea was a supercontinent during the late Paleozoic. It consisted of Gondwana, Euramerica, and Siberia. Pangaea was C-shaped. It stretched between Earth's northern and southern polar regions. Pangaea began to break apart about 200 million years ago. 180 million years ago, the western half of Gondwana separated. It created South America and Africa. The eastern half split apart to form Australia, Antarctica, India, and Madagascar. The sliding of tectonic plates creates diverse surface features. It creates mountains and volcanic island chains. Oceanic spreading creates a new ocean floor. The boundaries between tectonic plates are earthquake locations. The Hawaiian Islands arose as a mantle plume, delivered material to the surface. Lake Baikal formed when tectonic plates spread apart. No other known planet has plate tectonics. In space photos, Earth looks like a perfect sphere. So do all the other planets and stars. But in fact, our planet is far from perfect. First of all, why are planets spherical at all? The answer is gravity. Planets are formed bit by bit, over very long periods of time. Bits of matter bump into each other, forming bigger clumps. The bigger the clump, the stronger its gravitational pull. It draws in ever more matter, growing in size. When it's big enough, gravity starts smoothing it out. An object's gravitational pull always points toward the center of its mass. But gravity is actually surprisingly weak. A smaller object won't lose its shape. It takes a massive object to pull rock into shape. This is why smaller objects, such as comets, aren't spherical. But Earth is certainly big enough. So why isn't it perfectly round? A good example of Earth's imperfection is Mount Chimborazo. This mountain in Ecuador is Earth's highest point. However, it's 9,000 feet shorter than Everest. That's because Mount Chimborazo sits on the equator. Earth is squished at the poles and bulges out in the middle. So Chimborazo reaches 7,000 feet farther into the sky than Everest. The shape of our planet is technically oblate. That's like a slightly flattened sphere. That's because gravity isn't the only force affecting it. There's also a little something called the centrifugal force. This force is the opposite of the gravitational pull. It's directed outward and it's caused by Earth's rotation. You can see it in action too. If you spin around in a chair, you'll feel a pull away from your center. The same thing happens on a merry-go-round. All planets and moons spin in their orbits. So the centrifugal force causes them to bulge at their equators. The effect can be very subtle, but in some planets, it's very pronounced. Good examples of this are Jupiter and Saturn. Even in photos, you can see that the gas giants are slightly squished. Their middle bulges out noticeably as well. The reason we can see it is simple. They're the fastest spinning planets in our solar system. The faster something spins, the more the centrifugal force acts on it. An extreme example of the centrifugal force is Haumea. It's a dwarf planet in the Kuiper Belt. The Kuiper Belt is a region of icy objects outside Neptune's orbit. Haumea is about the size of Pluto, but it's spinning extremely fast, one complete rotation every 4 hours. As a result, it's almost egg-shaped. Earth's shape is further distorted by mountains and ocean trenches. Some trenches are more than 36,000 feet deep. Even sea level itself is irregularly shaped. Slight variations in Earth's gravity field create hills and valleys. The ocean's surface has permanent dips of over 300 feet. Additionally, the shape of the Earth is always changing. Sometimes this change is periodic. Daily tides, for example, affect both the ocean and the crust. Sometimes the change is slow and steady. Tectonic plates drift over millions of years. The crust rebounds after a heavy ice sheet has melted. Sometimes the shape of the planet changes in violent episodes, earthquakes, volcanic eruptions, or meteor strikes. So there's just no chance for Earth to stay round. Earth whirls around its axis at 1,000 miles per hour. It spins like a giant bowling ball, yet we don't feel a thing. This spinning gives us day and night in a seamless cycle. As Earth revolves, the sun appears to rise and set. This spin also helps the Earth's shape. It bulges outward at the equator. But what would happen if the planet stopped spinning? The consequences would be catastrophic. To put it mildly, our 24-hour days arise from Earth's spin. One full rotation equals one day-night cycle. If the spinning stopped, the day-night pattern would cease too. Instead of the sun rising and setting every 12 hours, it would stay fixed. One half of Earth would have constant daylight for 6 months. Then that same half would have 6 months of night. The sun-struck side would become a scorching desert. The dark side, a freezing tundra. But that's just the tip of the iceberg. The spinning Earth helps control wind patterns. Moving air follows the rotation of the Earth. If the Earth stopped spinning, winds would go haywire. Air would rush every which way. Areas at higher spin speeds would create hurricane-force gales. These winds would flatten forests like toothpicks. Let's not forget about the oceans. They cover 71% of our planet's surface. The Earth's spin keeps our oceans in control. Ocean currents follow the planet's rotation. As the moon orbits Earth, its gravity tugs on the oceans. This tug creates a bulge in the ocean on both sides of Earth. If the spin stopped, those currents would go rogue. Waters would surge towards the poles at first. Then swarms of tsunamis would batter the coasts. Waves could reach over 200 miles per hour. Low-lying zones like Florida would be completely submerged. Coastal cities would be demolished by the violent onslaught. The oceans would inundate huge inland areas too. They would continue roiling for weeks or months. But wait, there's more. The moon would go haywire without our planet's spin stabilizing its orbit. It might even escape our gravitational grasp and drift away. Then, there's the matter of vegetation. Plants need both day and night to survive. The day brings sunlight for photosynthesis. The night allows them to rest and reset. With 6 months of constant sun, then 6 months of total darkness, plants could not follow their natural cycles. Crops could not be cultivated in these conditions. Famine would quickly set in around the world. Trees, flowers, and grasslands would all wither away. And let's not discount the astronomical impacts. Earth has a magnetic field surrounding it. This invisible force field acts as a shield. It protects us from dangerous solar radiation. This magnetic shield gets its power from Earth's rotation. The spinning generates electrical currents. These currents create the magnetic field around our planet. If Earth's rotation stopped, so would the generation of currents. The magnetic field would decay rapidly. Radiation levels would soar to perilous amounts. Hazardous particles would bombard the entire planet. In essence, life as we know it would cease to exist. But what about the opposite scenario? What would happen if Earth started spinning faster? First of all, it would knock all satellites off track. Satellites fly around the Earth on set orbits. They have a speed that matches the planet's rotation. They stay positioned over the same spot all the time. If the planet speeds up, they won't be in proper positions. Satellite communications and broadcasting will be interrupted. Some satellites carry fuel. They may be able to adjust their positions and speeds, but others might have to be replaced. The Earth's spin creates centrifugal force. It is trying to throw you off the planet. For now, gravity is strong enough to keep you grounded. If Earth spins faster, the centrifugal force will increase. Imagine you weigh 150 pounds in the Arctic Circle. At the equator, your weight will be 149 pounds. That happens because of the extra centrifugal force. The faster the equator spins, the lower you weigh. The centrifugal force could make you weightless. For this, the equator has to speed up to 17,641 miles per hour. Everyone on Earth would be constantly jet-lagged. The faster the Earth spins, the shorter the days will be. A 1 mile per hour increase would make the day about a minute shorter. Your internal body clocks wouldn't notice it. The rotation has to be 100 miles per hour faster to have an impact. Then a day would be about 22 hours long. Your body won't be able to adjust to the change. This would harm plants and animals too. Hurricanes would get stronger. Earth's rotation carries the atmosphere with it, but temperature difference is the main driver of winds. We wouldn't notice a big difference in weather patterns. However, extreme weather would be more destructive. Hurricanes will spin faster, and there will be more energy in them. If the Earth wasn't spinning, winds would blow in a line. They'd go from the North Pole straight to the equator. The spinning gets the winds to deflect eastward. The curvature of the winds gives a hurricane its spin. If the Earth spun faster, the winds would deflect further. Moreover, the ocean water would start to amass at the equator. At 1 mile per hour faster, the water would get a few inches deeper. It might take a few years to notice the change. At 100 miles per hour faster, the equator would start to drown. The Amazon basin in northern Australia would go underwater. At 1,000 miles per hour faster, the equator would be covered with water. Only the highest mountains would still be visible. That extra water would be pulled out of the polar regions. There the centrifugal force is lower, so the Arctic Ocean would be a lot shallower. The air would be heavy with moisture. There would be constant fog and rain at the equator. At 17,000 miles per hour, the centrifugal force would match gravity. Droplets of water would move up in the atmosphere. Ultimately, seismic activity would rock the entire planet. At about 24,000 miles per hour, the Earth's crust would shift. It'll flatten out at the poles and bulge around the equator. The tectonic plates would move quickly, so there would be enormous earthquakes. Thankfully, this is a very unlikely scenario.